here I've got a mirror. Right now it's curved so it is concave to our object, which is a candle. And over here I've got a screen onto which I can project the light. Let's go ahead and light the candle so it becomes a source of light. And you can see we're getting an image onto the screen. If we can get it onto the screen, what sort of image must this be? That's real. This is what it means to have a real image. The light is reflecting off the mirror and it really is converging onto the screen. Notice, how does it appear? Hopefully you can see it's upside down. The flame, of course, rises above the candle like that. This appears to be upside down. It's clearly inverted. Remember, for a single optical device, real images are always inverted. What about the size of it? Well, hopefully you see it's a really large image of the flame compared to the actual size of the flame. That's a magnified image. In fact, this situation is the very first ray diagram that you drew where the object distance was in between f and 2f. We got a real inverted magnified image. So I'm going to move things around a little bit. Okay, once again, getting a magnified image, still real, still inverted. Still real, still inverted. Still real, still inverted, but you can see it's sort of getting smaller, right? The image is not as magnified before. In fact, maybe it's about life size now. And now you should see that the image is smaller than the object itself. And you notice that now the object and the optical device are farther apart than they were before. This is the first ray diagram we did in problem number 2, where SO was larger than twice F. We got a real, inverted, reduced image. Let's move it in pretty close. So if I move the object very close to the mirror, you can see on the screen, all we get is a big blob of light. We're not going to be able to get an image on the screen because look how close the object is to the optical device. Right now, SO is smaller than F. Now we can see the image if I move this around this way. Now, you can look at the mirror and you should definitely see the virtual image. It is clearly upright. If it's upright, it must be virtual. And maybe it's a little bit magnified, right? This is the example we did in problem 3, where SO was less than F. So the object is within the focal length, this converging concave mirror. That's when you get a virtual upright image. If I flip the mirror around, it's now convex. And again, we get just basically the whole screen gets illuminated. There's really nothing I can do, nowhere I can put this mirror. I'm moving the mirror back and forth. There's nowhere I can put it where I'm going to get a focused image on the screen because it is a convex mirror. It is diverging. Diverging mirrors only do one thing. They only produce virtual, upright, and reduced images. And now when I turn it this way, you can see the image of the candle. You can see it's upright, which means it's virtual, and certainly a bit reduced compared to the actual object. No matter where I put the object, no matter where I put the mirror, it's always going to be upright, virtual, and reduced for this diverging mirror.